beneath the thin hush of Earth's atmosphere, beyond the soft veil of stars, the universe opens into a silence so vast it feels infinite, a silence unbroken, save for the slow pulse of ancient light. Here, beyond the spirals of galaxies and the filaments of clustered worlds, the cosmos drifts into a darkness without horizon. It is not a place that ends, but a question without an answer. For millennia, the human mind has strained against its own boundaries, lifting its gaze from the dust of its origin to the heavens above, searching for an edge, to stand on a world so small, and to ask whether all of existence has a frontier is to weigh the finite against the eternal. We are fleeting sparks within a furnace that has burned for nearly 14 billion years. And yet, the question persists. Stubborn as gravity itself, does space have an ending? Does time itself? Or are these only illusions born of minds too young to understand infinity? The universe answers not with words, but with light. Photons, released in the primal fire of the Big Bang, have traveled across gulfs of darkness longer than Earth has existed, carrying whispers of the past. They pass through voids vast enough to swallow clusters of galaxies, bent by gravity, scattered by dust, and yet they endure. To peer at them through a telescope is to look not into distance, but into history. Every star is a message delayed, every galaxy an echo from an earlier age. The further we look, the younger the universe becomes, until light itself fails us, reaching the veil of cosmic dawn. Beyond it, we see no further. But perhaps the greater mystery is not in how far light can travel, but in where it might ultimately arrive. Does it fade into a final darkness, into some boundary where existence itself is undone? Or does it circle endlessly in a cosmos without borders, where beginnings and endings are illusions of perception, like mirages on a desert horizon? If one could travel without limit, chasing the speed of light across billions of years, would the journey lead to a wall, a void, or back to the place where it began? The human mind trembles at the thought, a frontier beyond all frontiers, the last horizon. At that edge, if it exists at all, waits the most profound of truths, whether the universe itself is finite, or whether we, like light, are destined to wander forever through an infinity without end. The night sky has always appeared boundless, an ocean of scattered fire that stretched far beyond the reach of thought. For centuries, the first telescopes brought only confirmation of mystery. Each time glass was polished a little finer, each time mirrors were ground a little smoother, the heavens deepened. Stars, once thought to be singular, multiplied into clusters. Wisps of light revealed themselves as galaxies, each containing hundreds of billions of suns. The more humanity looked, the more the universe unfolded, like a scroll that would not end. But in 1929, Edwin Hubble uncovered a revelation that altered not just the scale of the cosmos, but its nature itself. By measuring the faint signatures of distant galaxies, he found that their light was stretched, reddened, drawn out across space. The deeper he looked, the faster the galaxies seemed to recede. The universe, it seemed, was not static. It was expanding, like a vast fabric being pulled in every direction at once. There was no center to this growth, no privileged vantage point, only a restless stretching of space-time itself. This discovery suggested something profound. The cosmos was not eternal and unchanging, but dynamic, born from an origin point billions of years ago. Yet even in this revelation lay a boundary. Light, though swift, is finite. It has traveled no longer than the universe has existed. At 13.8 billion years of age, the observable universe is drawn not by walls of matter, but by the limits of time itself. Beyond that horizon, galaxies may exist, but their light has not yet arrived. To To look out across space is therefore to look backward across history, each layer of light peeling away the ages until, finally, the view reaches a barrier that no telescope can pierce. The afterglow of creation, discovered by accident in 1965, the cosmic microwave background, a faint, nearly uniform radiation saturating the sky, is the oldest light the universe allows us to see, released just 380,000 years after the Big Bang, when the first atoms formed and the cosmos became transparent. It is a frozen memory of the moment when darkness gave way to light. Modern instruments like the Planck satellite have mapped this glow in exquisite detail, revealing not perfect smoothness, but tiny fluctuations, ripples of density that would one day grow into galaxies, clusters, and the vast cosmic web. With each advance, the Hubble Space Telescope, the James Webb, the deep surveys of Planck vision reaches further, closer to the cosmic dawn. But even at their limit, the horizon remains. A universe 93 billion light-years across can be seen. Yet, it is not the full cosmos, only the fragment visible from here at this time. Beyond that edge lies the unknowable, regions forever hidden, where light will never reach us. And so, the first true glimpses of cosmic boundaries emerge. They are not solid walls of stone or flame, but horizons of time and light, frontiers written into the nature of existence itself. Each photon collected by human instruments is a messenger from the past, whispering of beginnings, and hinting that the end may be a horizon always retreating. Never reached, the universe, revealed through these breakthroughs, became something stranger than any myth. No longer a silent dome of stars, it was now a living, changing expanse. The expansion discovered by Hubble was not an explosion flinging matter outward into emptiness. It was the stretching of space itself, carrying galaxies apart like driftwood on a rising tide. The farther away they were, the faster they seemed to vanish from sight, until, at great enough distances, their light stretched beyond visibility altogether, slipping into wavelengths the human eye could never see. In this, the universe revealed its first true limit, not of structure, but of perception. The cosmic microwave background offered the second, though it appears uniform to the naked eye. Advanced instruments show it to be a mosaic of faint fluctuations, temperature differences of less than a millionth of a degree. Yet these tiny imbalances shaped everything that followed. Denser regions became the seeds of galaxies. Voids stretched between them to form the cosmic web. In its faint glow, scientists see not only a relic of creation, but a blueprint of all that was to come. To study the CMB is to glimpse the first whispers of order rising from chaos, but the boundary it represents is sobering. Before the universe cooled enough for light to travel freely, space was shrouded in a dense fog of particles. Photons collided endlessly, trapped in a storm that kept the cosmos opaque. No telescope, however powerful, can see through this veil. It is a curtain drawn across the earliest chapter of existence, hiding the instant of birth. What lies before it can only be inferred through theory and mathematics, through models built on the physics of the very small and the very vast. It is here that speculation and observation meet in the struggle to reach beyond the horizon of light. The spacecraft that extend human vision are more than machines of metal and glass. They are instruments of time travel. The Hubble Space Telescope unveiled galaxies so faint and so distant that their light began its journey when Earth was still young. The James Webb, with its golden mirrors, peers further still, into an era when the first stars ignited and galaxies assembled from clouds of hydrogen. And the Planck Observatory, by mapping the CMB with exquisite precision, has given the most accurate picture yet of the universe's infancy, measuring its age, its contents, and its rate of expansion together. These instruments weave a narrative that edges ever closer to the beginning. They confirm a cosmos filled not only with matter and light, but with hidden ingredients, dark matter, shaping galaxies through its unseen gravity and dark energy, driving the acceleration of expansion across the whole of space. These discoveries deepen the sense of mystery. For if the observable universe is defined by light, then what of these unseen forces that shape its destiny? They extend the question of limits beyond the horizon of sight into realms of the unknown. And still, the great horizon remains. Beyond the 13.8 billion year wall of the CMB lies a region forever concealed, where the very laws of physics may take forms unimagined. If space is infinite, then the observable universe is but a fragment, a small island in a sea without end. If space is finite yet unbounded, it may curve back upon itself, like the surface of a sphere, so that a journey long enough might return to its origin. Both visions stretch the human mind to breaking point, leaving open a riddle without conclusion. Every new observation sharpens the paradox. The universe is both comprehensible and unknowable, measured with extraordinary precision and yet shrouded in mystery. Humanity now knows its age to a margin of less than 100 million years, a fraction of cosmic time. It knows the rate at which space expands, the balance of matter and energy, the shape of fluctuations in the infant cosmos. And yet, the simple question remains unanswered. Does it end? Or does it continue without limit, beyond every horizon light can ever cross? Thus, breakthrough observations have given humanity its first tangible map of the infinite, not a chart of continents and seas, but of time and distance, of light and silence. They reveal a universe with horizons drawn not in stone, but in the physics of perception itself. To stand at the edge of the observable cosmos is to look upon the furthest wall that sight can reach, while knowing, with quiet awe, that the true vastness begins just beyond. Infinity, when spoken aloud, feels almost like a trick of language, a concept so vast the mind can only brush against it before recoiling. The universe embodies this paradox. On the one hand, the observable cosmos is measurable, finite, bound by the 13.8 billion years that light has traveled to reach us. Yet beyond that horizon stretches the unknown, perhaps endless, perhaps curved back upon itself. Space may have no boundary, but our sight always does. And in that gap between what is visible and what may exist lies the greatest of mysteries. Time itself seems more fragile, more easily fractured into beginning and end. All evidence points back to a singular origin, the Big Bang, when the universe emerged, not from an explosion in space, but from the sudden expansion of space itself. With astonishing precision, science can trace the evolution of that expansion, from the birth of the first atoms to the sculpting of galaxies. Yet the question remains, if time had a beginning, must it also demand an end? Or does it, like space, stretch forward into an infinity that no observer will ever see? The discovery of dark energy in 1998 cast that question into sharper relief. By measuring the faint glow of supernova in distant galaxies, astronomers expected to find that cosmic expansion was slowing under the pull of gravity. Instead, they uncovered the opposite. The universe was not only expanding, but accelerating. Some unknown force, making up nearly 70% of the cosmos, was pushing galaxies apart faster and faster. This invisible pressure, dark energy, remains unexplained, yet its implications are profound. If it continues unchecked, galaxies will drift forever beyond one another's reach. Stars will burn out. Matter will thin into darkness. A universe without end, but also without renewal. And yet another paradox lurks in the background, the cosmic horizon problem. When scientists study the cosmic microwave background, The faint afterglow of the early universe, they find it astonishingly uniform. Regions separated by vast distances, too far to have ever exchanged light or energy, appear nearly identical in temperature. How could parts of the cosmos that were never in contact share the same conditions? This puzzle suggests something deeper, that our vision captures only a sliver of a reality, shaped by processes beyond our comprehension. Perhaps by inflation, a rapid expansion in the first moments of time that smoothed the universe into its present form. What we see, then, may be only a fragment of a larger truth. Our observable universe, stretching 93 billion light-years across, could be a mere pocket of something far greater, a bubble in a sea of countless others, or a sheet in an infinite expanse. The mystery deepens not in scale alone, but in meaning. To ask how big is the universe is no longer sufficient. The question now becomes, what lies beyond the edge of perception? Each discovery sharpens the riddle rather than resolves it. The observable cosmos is vast yet finite. Time has a beginning yet no assured conclusion. Dark energy drives expansion yet remains invisible. And distant regions appear connected without ever having touched. The answers elude certainty, but they reveal the universe not as a solved equation, but as a living paradox, a reality where horizons are not ends, but invitations to imagine what cannot yet be seen. The mystery of infinity is not merely one of distance, but of fate. If the expansion of the universe continues to accelerate, then with every passing billion years, more and more of the cosmos will vanish from view. Galaxies will slip beyond the horizon, their light stretched into wavelengths so long that no instrument could ever catch them. To future observers, the night sky will dim, until only the nearest cluster of galaxies remains. The universe will appear smaller, quieter, lonelier, though in truth it will be larger than ever. Infinity, in this scenario, becomes isolation. Yet the story is not written in certainty. Dark energy, though measured in its effect, remains unknown in its essence. It could be a constant property of space, a pressure that never fades. Or it could shift over time, strengthening or weakening in ways that alter the destiny of everything. If it grows stronger, the acceleration may tear apart galaxies, then stars, then even the atoms themselves in a finale known as the Big Rip. If it diminishes, gravity could one day slow expansion, halting it, reversing it, and leading to a big crunch, a collapse as dramatic as the beginning itself. And if it fluctuates, the universe might oscillate endlessly, a cycle of births and deaths without finality. Each possibility reframes the question of infinity not as a single path, but as a spectrum of cosmic futures. Behind these speculations lies a deeper unease, the realization that the observable universe might be only a fragment of a grander design. Inflation theory, the idea that the universe expanded exponentially in its first fractions of a second, offers an explanation for the horizon problem, showing how distant regions could once have been in contact before being driven apart. But inflation also carries with it a more staggering implication. If space can inflate once, it may do so again and again in countless regions, giving rise to an endless tapestry of pocket universes. In such a multiverse, what is seen from Earth is but a single bubble, one island in an ocean beyond imagining. This vision forces a shift from scale to meaning. For if the cosmos extends endlessly in space, time, and variation, then the very notion of an edge dissolves. The limits humanity encounters are not boundaries of reality, but boundaries of perception, of tools, of physics as currently known. The horizon that frames the observable universe is like the surface of a vast fog, not the end of the world, but the beginning of mystery. Beyond it, conditions may be unimaginably different, other distributions of matter, other laws of physics, perhaps even other versions of time itself. Here lies the philosophical weight of modern cosmology. Each breakthrough, Hubble's expansion, the CMB, the discovery of dark energy, has not closed questions, but widened them. With each step deeper into the unknown, certainty retreats, replaced by paradox. Infinity without end, yet observation with limits. Time with a beginning, but no assured conclusion. A cosmos, uniform in appearance, yet too vast for its regions ever to have touched. What emerges is not a picture of resolution, but of an enigma sharpened to brilliance. To confront these mysteries is to realize how deeply human understanding remains bound to perspective. The universe may have no wall, no boundary, and yet every observer finds themselves at the center of their own horizon, surrounded by the visible past. What lies beyond may never be directly seen. It may exist forever outside the reach of light, a hidden expanse that resists all inquiry. Yet, in the silence between galaxies, in the faint glow of ancient radiation, the question persists. The search itself becomes the story, not the discovery of an ending, but the endless unfolding of wonder, long before mathematics traced the curvature of space, long before instruments captured the afterglow of creation. The question of cosmic limits haunted the human imagination. Ancient civilizations gazed upward and filled the silence with myth. For the Greeks, the word cosmos meant order, a harmonious structure that set boundaries to chaos. In India, the Vedic hymns spoke of endless cycles of creation and dissolution, universes born and reborn like breaths of a divine being. The Mayans imagined layered heavens and underworlds, stacked like steps of an infinite pyramid. The Egyptians envisioned the goddess Nut arching her body over the world, her skin scattered with stars, a living boundary between earth and sky. Each culture reached for a story to contain the unimaginable, shaping infinity into forms the mind could hold. But these visions were only preludes. As instruments grew sharper and thought more rigorous, the universe began to resist its mythic cages. The Copernican revolution in the 16th century was the first fracture. Earth, once believed to be the still center of all creation, was displaced, revealed as one planet among many, circling the sun. The cosmos was no longer a closed sphere with mankind at its heart, but an open system, fluid and redefined. The boundary had shifted outward, leaving behind both awe and unease. Then came Galileo, who lifted a small telescope to the night and changed the scale of wonder forever. Through his lens, the Milky Way dissolved into countless stars, too numerous to imagine. Jupiter revealed moons circling its massive bulk, a miniature system echoing the heliocentric order. The heavens were no longer perfect spheres, but worlds upon worlds, governed by the same physics as Earth itself. With each observation, the universe grew larger, older, stranger. Boundaries dissolved into horizons that receded with every new glance. The first attempts to measure cosmic distances added a new layer of revelation. Stellar parallax, the shifting of stars against the background sky as Earth moved in its orbit, revealed that even the nearest suns lay at unfathomable distances. Cepheid variables, stars whose rhythmic pulsing revealed their true brightness, became lighthouses for gauging galaxies across space. The scale of the cosmos stretched beyond comprehension, expanding faster than imagination could adjust. The heavens, once thought to be a crystalline sphere only a few thousand miles above, now loomed as a gulf so immense that light itself needed years, centuries, millennia to cross it. And still the questions deepened. In 1915, Albert Einstein unveiled general relativity, a theory that transformed space and time from empty backdrops into dynamic fabric. Matter told space-time how to curve, Space-time told matter how to move. Gravity was no longer a force pulling across distance, but the bending of the very stage on which existence unfolded. With this came a possibility that startled even Einstein. The universe itself could not be static. If space-time was a fabric, it could stretch or contract. The cosmos itself could be alive with motion. The early 20th century became a battleground of ideas. Some physicists clung to the vision of a steady-state universe, eternal and unchanging, infinite in both directions of time. Others, following the equations of relativity, saw the hints of expansion, a cosmos with a beginning. The first evidence was still faint, glimpses in red-shifted light and patterns in the distribution of galaxies. Yet the debate revealed a profound shift. Humanity was beginning to move from myth into measurement, from allegory into physics, from stories of gods and cycles into questions of energy, curvature, and time. What emerged from these early discoveries was not merely a larger universe, but a universe without precedent in human thought. The myths of antiquity, the philosophies of the ancients, had spoken of boundaries as walls, ceilings, or cycles. The new science suggested something stranger, that limits might be illusions born of perception, that the cosmos could be vast beyond reach, and that time itself might have flowed from an origin point. From Galileo's telescope to Einstein's equations, the stage was being set for a revelation that would break the last remnants of the old sky and reveal a universe not just immense, but dynamic, expanding, and without a center. The thread of discovery did not move in a straight line, but through debate, error, and the slow sharpening of evidence. In the early 20th century, the scale of the universe itself was contested. Astronomers argued whether the faint spiral nebulae seen through telescopes were clouds of gas within the Milky Way, or whether they were entire island universes of stars beyond our own. This clash reached its height in 1920, in what became known as the Great Debate between Harlow Shapley and Huber Curtis. Shapley believed the Milky Way was the whole of the cosmos, vast but self-contained. Curtis argued that the spirals were other galaxies, each as immense as the Milky Way itself. At the time, evidence was thin, and certainty remained elusive. Yet in the years that followed, the truth emerged. The spirals were galaxies, and the universe was staggeringly larger than once imagined. This realization was not simply a matter of numbers, of billions upon billions of stars. It was a shift in perspective as profound as Copernicus. Humanity's home was no longer the center of a single galaxy, but a speck among countless others scattered across space. The known universe grew not by steps, but by leaps, each new measurement stretching the horizon farther away, leaving the mind grasping for footholds. It was Edwin Hubble who finally measured this truth with clarity. By studying Cepheid variables in the Andromeda galaxy, he calculated its distance far beyond the Milky Way. The spiral nebulae were no longer within, but beyond. The cosmos had multiplied in size, its scale slipping into a realm almost ungraspable. With Hubble's work, the universe became a landscape of galaxies, each containing billions of suns, each separated by oceans of darkness. But Hubble's greatest discovery was yet to come. In 1929, through painstaking measurement of galactic spectra, he revealed that the farther away a galaxy lay, the faster it receded. The universe was expanding, every galaxy carried along as though on the surface of a balloon being stretched. This revelation shattered the last remnants of the steady-state idea. The cosmos had a history, a trajectory, and, by implication, a beginning. For Einstein, this was both vindication and discomfort. When first developing general relativity, he had introduced the cosmological constant, a mathematical term meant to stabilize the universe against collapse or expansion. He had assumed the cosmos must be eternal, unchanging on the grandest scales. Hubble's discovery revealed that assumption to be flawed. The universe was not static. It had grown from something smaller, denser, hotter, what Einstein had once added to preserve balance. He later called his greatest blunder. Yet, ironically, the cosmological constant would return decades later, reincarnated in the mystery of dark energy. The transition from ancient myth to scientific cosmology was more than an intellectual shift. It was a reordering of humanity's place within existence. The Greek spheres, the Mayan heavens, the Egyptian goddess arching over the earth, all had given meaning by placing the cosmos within reach of imagination. The revelations of Hubble, Shapley, and Einstein replaced these structures with something far colder, but also far more profound, a universe that cared nothing for human boundaries, yet offered truths more vast than myth had dared to contain. As instruments sharpened, the skies grew more eloquent. The Milky Way became a single thread in a cosmic web. Distances once measured in miles became measured in light years, then millions of light years, then billions, and with each layer revealed, the question of limits grew sharper. The myths had spoken of boundaries as walls. The ancients had imagined cycles that reset with divine rhythm. But the new science was hinting at something stranger, a universe that stretched, a fabric that curved, a space and time that obeyed laws no culture had foreseen. By the early 20th century, the stage was set. The ancient stories had given way to mathematics, telescopes, and evidence. The universe, no longer a dome overhead, had become a frontier without clear end, a riddle that only deepened with every answer. The revelation came with the quiet gravity of numbers, yet it landed with the weight of a thunderclap. When Edwin Hubble announced that distant galaxies were receding, and that the farther they were, the faster they fled, the very foundations of cosmology shifted. The universe, once imagined as eternal and unchanging, had been caught in motion. Space itself was expanding. For a community long accustomed to picturing the cosmos as a serene and fixed backdrop, the implications were staggering. The universe was not a stage, but an actor. Not a still painting, but a story in motion. Even Einstein had resisted this vision. When his equations of general relativity first suggested a dynamic universe, he bent them with an extra term, the cosmological constant, a mathematical device to hold the cosmos in balance. The idea of an evolving universe seemed too disruptive, too far from the elegance of eternal symmetry. But the sky refused to bend to preference. Hubble's discoveries stripped away the illusion of stasis, and Einstein conceded. He would later call his attempt to preserve a static cosmos his greatest blunder. Yet, in a twist of irony, the cosmological constant would resurface decades later, reimagined as dark energy, the hidden force accelerating the very expansion it was once meant to restrain. The 1960s brought another revelation, one even more difficult to ignore. A faint hiss of microwave radiation, discovered accidentally by Arno Penzias and Robert Wilson, filled every corner of the sky. This was no ordinary interference, but the fossil light of creation itself. The cosmic microwave background was proof that the universe had once been hot, dense, and opaque, a fiery origin imprinted in radiation that still lingers nearly 14 billion years later. With this, the last refuge of the steady-state universe collapsed. The cosmos had a beginning. Time itself had a birth. For many, this realization was as unsettling as it was thrilling. A universe with a beginning suggested questions that edged into philosophy, even metaphysics. What had existed before? Could before even exist if time itself had only just begun? For scientists trained to think in empirical terms, these questions were uncomfortable, yet unavoidable. The idea of eternity had been comforting, a cosmos without origin, stretching forever in both directions. A universe with a boundary in time was more fragile, more haunting. Philosophical resistance ran deep. Fred Hoyle, one of the most prominent advocates of the steady-state theory, mocked the new model with the dismissive term Big Bang, never imagining the name would endure. To him, the notion of creation smacked of theology, of myths reborn in scientific guise. Yet the data gathered strength. The microwave background, uniform across the sky yet flecked with tiny fluctuations, aligned with predictions of an expanding, cooling universe. What began as ridicule hardened into reluctant acceptance. The cosmos had written its history in light, and that record could not be ignored. For the human imagination, trained to think in finite scales, these discoveries posed challenges as profound as they were exhilarating. Infinity had once been handled with myth, gods, cycles, and boundaries that made the incomprehensible manageable. Now, science was forcing thought into new terrain. Space without center, time with a beginning, galaxies fleeing into a future no I could follow. These were ideas that bent perception itself. Cosmology, once an intersection of philosophy and myth, began to crystallize into a scientific discipline. It blended astronomy's observations with physics laws, mapping the origins and fate of the universe with tools of measurement and mathematics. Yet even as it grew more rigorous, its questions retained a philosophical weight. What is the nature of time? How far does space extend? Is infinity real, or only an illusion of perspective? The first scientific reactions to these discoveries were not merely debates over data. They were reckonings with meaning. To live in a static, eternal universe was to live in a cosmos indifferent to time, where existence itself was unchanging. To live in a universe with a beginning was to live in a story, a narrative with chapters still unfolding. Humanity was no longer a spectator in a frozen sky, but part of a dynamic, evolving whole, bound to the same currents of time that had shaped galaxies and stars. And so, in the shock of discovery, cosmology was born anew. It was no longer the study of stars alone, nor the recitation of myths, but the attempt to grasp the infinite with the tools of science. A field that asked not only what was visible, but what might lie beyond the reach of light itself. The transformation of thought did not unfold in an instant. Even after Hubble's observations, after the equations of relativity had pointed to expansion, disbelief lingered like a shadow across the halls of academia. The scale of the claim was too vast, the implications too profound. To admit that the universe was in motion meant accepting that it was not infinite in age, that there had been a moment when the cosmic clock began to tick. For many, this was less a scientific conclusion than a philosophical upheaval, demanding the abandonment of ideas that had stood unchallenged for centuries. The cosmic microwave background shifted the weight of evidence irreversibly, but its interpretation ignited heated exchanges. If the universe had once been a searing ocean of plasma, then the galaxies, stars, and planets seen today were the frozen remnants of that inferno, cooled by the expansion of space itself. This suggested not only a beginning but a process, a transformation of matter and energy unfolding over eons. The data offered beauty and coherence, yet also discomfort. A universe with an origin carried an unsettling fragility, as though existence itself were a temporary arrangement. Some clung to the steady-state model, hoping to preserve eternity. In that vision, new matter was continually created as galaxies drifted apart, maintaining a universe that was unchanging on the largest scales. It was a picture that spared the mind from contemplating beginnings or ends. But as radio astronomy advanced, it revealed a cosmos populated with quasars, ancient brilliant beacons scattered through deep time, yet curiously absent in the nearby more recent universe. Their distribution betrayed change, not permanence. The sky was telling a story that no steady state could hold. Others began to see elegance in a universe with a beginning. The Big Bang did not just explain expansion and background radiation, it tied together the chemistry of the cosmos. The very atoms of life, hydrogen and helium, forged in the first minutes, and heavier elements later born in stellar furnaces, were chapters in the same unfolding tale. The story of galaxies, planets, and even biology became threads in a single tapestry stretching back to the same primordial moment. What had begun as resistance transformed slowly into awe, yet acceptance did not erase unease. To ask what lay before the Big Bang was to stare into the void of unanswerable questions. Was the beginning absolute, or merely the threshold of a larger reality hidden from view? Theories multiplied. Some imagined a universe emerging from quantum fluctuations, a sudden burst of order from the restless sea of the vacuum. Others spoke of cycles, of a cosmos eternally collapsing and reborn. Each expansion only one breath in an endless rhythm. Each idea sought to reconcile the finite with the infinite, to place boundaries around the unbounded. In this period, cosmology itself became a bridge between science and philosophy. No longer confined to describing stars and their motions, it ventured into the nature of time, the shape of space, and the fate of all existence. Equations became a kind of poetry, telling of a universe vast beyond measure yet grounded in laws of symmetry and motion. Observations were no longer just catalogues of light, but glimpses of an origin imprinted in every photon. The reactions of the scientific community reflected more than intellectual caution. They revealed the difficulty of reshaping human imagination. For millennia, eternity had been the safe horizon of thought. Now, science had replaced eternity with story, and with story came tension, uncertainty, and mystery. The cosmos was not fixed, but alive with history. It possessed not only scale, but age. It was not infinite in all directions of time, but stretched between a fiery birth and an unknowable future. In this way, the early decades of the 20th century marked more than a turning point in science. They marked a turning point in human self-perception. To acknowledge an evolving universe was to acknowledge that everything, stars, galaxies, even consciousness itself, was transient. What had seemed eternal was revealed as fleeting, bound to the same expansion that carried galaxies into the darkness. Humanity, once at the imagined center of a static cosmos, now found itself a brief flame in an ever-unfolding ocean of change. The first reactions to these discoveries, with their disbelief, resistance, and eventual wonder, were not just the story of science grappling with data. They were the story of a species awakening to a new understanding of reality itself, a recognition that the universe is not an unchanging temple, but a living, breathing cosmos still in motion. Still becoming. The discoveries of the early 20th century left the scientific world with a revelation and a riddle. The universe was not fixed. It was expanding, restless, alive with motion. Yet with this new truth came an inevitable question. If the cosmos is growing, then what awaits it at the end of its journey? Would expansion continue forever, carrying galaxies into eternal solitude? Or would gravity one day reclaim its dominion, drawing everything back toward a final collapse? The first investigators of these mysteries turned not only to telescopes, but to mathematics itself. Einstein's equations, and the refinements that followed, became a stage upon which cosmic fates were played out in abstraction. Within those equations, three possible destinies emerged. If matter filled the universe densely enough, gravity would one day halt the expansion and pull everything inward again. A closed universe, doomed to contract into a big crunch. If matter were too sparse, Expansion would never cease, an open universe, growing colder, emptier, without end. Between these two extremes lay the fragile possibility of a flat cosmos, balanced on the knife's edge, expanding forever but always slowing, never collapsing, never stopping. For a time, each possibility was considered with equal weight. Scientists drew diagrams of universes that curved like spheres, universes that stretched into open saddles, and universes that extended flat and infinite in all directions. Geometry was no longer a matter of abstract lines and shapes. It became a window into the destiny of all existence. To measure the shape of space was to glimpse the future of time itself. The concept of oscillating universes soon followed. If the cosmos collapsed into a big crunch, could that collapse spark a new Big Bang? Could existence itself be cyclical, with endless eons of expansion and rebirth, like a cosmic heartbeat? The idea was both elegant and unsettling. A universe without a true beginning, without a final end, but bound to an eternal rhythm beyond human comprehension. Though speculative, the vision carried a deep resonance, a universe less like a machine, more like a living organism, pulsing through infinite ages. But every vision of destiny eventually circled back to thermodynamics. The second law whispered of entropy, of energy dispersing, of order decaying into disorder. If expansion carried on indefinitely, galaxies would burn out, stars would die, and even black holes would eventually evaporate through Hawking radiation. What remained would be darkness and silence, the heat death of the universe, where temperature approached uniformity and motion ceased. It was a fate as haunting as it was inescapable under the laws of physics, an eternal stillness after a brief blaze of creation. Yet other interpretations pushed against inevitability. Perhaps entropy did not spell a final doom, but rather a transformation yet unknown. Quantum physics, even in its infancy, hinted that the vacuum itself was restless, that the emptiness of space might hold energies not yet understood. If so, perhaps death was not the end, but a threshold to another kind of genesis. The geometry of space offered another paradox. Einstein himself suggested that the universe might be finite but unbounded, like the surface of a sphere, where one can travel endlessly without encountering an edge. Such a vision dissolved the human craving for walls and borders. The universe could be whole without needing boundaries, infinite in journey but finite in content. This idea blurred the line between mathematics and philosophy, offering a cosmos that could be both comprehensible and forever mysterious. These early investigations revealed more than the possible fates of matter and light. They revealed the limits of human imagination. Each model, each theory, was not only a scientific attempt to describe reality, but a mirror reflecting the desire to find meaning in vastness. Would existence fade into silence, repeat in cycles, or stretch onward without closure? No data yet could decide, and so the universe became a canvas for possibility. The scientists who wrestled with these questions recognized that their tools were incomplete. General relativity described the grand sweep of space-time, but it faltered at the smaller scales, where quantum uncertainty reigned. To understand the true limits of space and time, both frameworks would need to merge into something greater, a union of the vast and the minute, the smooth fabric of relativity with the restless quanta of physics. The search for that unifying theory became more than a mathematical pursuit. It became a philosophical necessity in this tension between equations and imagination. Between certainty and wonder, the universe revealed itself as both knowable and elusive. The early visions of fate and geometry may not have given final answers, but they framed the questions that continue to guide cosmology to this day. In asking how space curves, how time ends, and whether existence itself breathes in cycles. Humanity was not merely studying the universe. It was, perhaps for the first time, beginning to listen to it. The first explorations of cosmic fate were not only exercises in physics, but journeys into philosophy. To suggest that the universe could one day collapse upon itself, or that it might thin into endless silence, forced a confrontation with the human instinct to search for permanence. Eternity had long been the canvas upon which myths and religions painted their visions. Now science was daring to sketch scenarios where even eternity might not endure. As debates unfolded, the very act of defining the universe's geometry carried with it a sense of spiritual weight. If space was curved like a sphere, then perhaps existence was contained, whole, and comprehensible. If it bent outward like a saddle, then perhaps it stretched endlessly, without walls or boundaries. To imagine a flat universe was to embrace the unnerving notion of infinity, stretching without limit, yet balanced with exquisite precision on a razor's edge. Each possibility carried with it a reflection of human longing for closure, for balance, or for unending horizons. The idea of oscillating universes, cycles of collapse and rebirth, drew its strength from this desire for continuity. A cosmic heartbeat, pulsing eternally, seemed to answer the fear of finality. If one universe died, another would rise, endlessly renewing existence. Yet such visions were shadowed by entropy, the whisper of decay woven into every process of nature. Could cycles continue forever in defiance of the second law of thermodynamics? Or would each rebound carry less energy, each rebirth a fainter echo, until even eternity grew weary? The questions could not yet be answered, but they lingered like ghosts at the edge of every calculation. Meanwhile, the concept of heat death, the spreading of energy into uniform stillness, became a haunting counterpoint. It was a fate not marked by fiery destruction, but by silence. No dramatic collapse, no thunderous rebirth, only the slow extinguishing of light, the quiet scattering of matter until nothing meaningful remained. For many, it was the bleakest vision, a universe not ending with a bang, but dissolving into eternal dusk. And yet, there were glimmers of hope even within this vision of decay. The new mathematics of quantum theory suggested that the vacuum itself might not be empty, but alive with fluctuations, with possibilities yet unseen. Could the so-called void harbor energies that might one day spark renewal? Could the very laws of physics themselves evolve, changing the script of destiny in ways not yet understood? These speculations reminded scientists of the fragility of their knowledge. Observations extended only so far, and equations, though elegant, rested on assumptions about regions of the cosmos never directly seen. To speak of the universe's fate was to gaze across gulfs of uncertainty. Yet even with so little certainty, the attempt itself was profound. For in wrestling with the destiny of galaxies, humanity was wrestling with its own impermanence. The debates also highlighted the incompleteness of the frameworks at hand. Relativity could describe the curvature of space-time on grand scales, but it dissolved into paradox near singularities, where density and gravity became infinite. Quantum mechanics, with its rules of uncertainty and probability, worked beautifully at microscopic levels, but resisted extension to the cosmos as a whole. The recognition grew that a deeper synthesis was required, a theory that could unify the smooth geometry of relativity with the restless fluctuations of the quantum world. Without such a theory, the final fate of the universe could never be more than conjecture. This tension between knowledge and ignorance lent the early investigations a sense of humility. The cosmos seemed to invite description, but not surrender its secrets completely. Every answer revealed new layers of mystery. If the universe was finite but unbounded, then where did that leave the human need for borders? If it oscillated endlessly, what gave rise to the first cycle? If it were destined for heat death, what purpose did its brief, radiant epochs of galaxies and stars truly serve? The early models did not resolve these questions, but they shaped the framework of thought. They taught that the universe could not be imagined in simple terms of beginnings and ends, of edges and boundaries. It demanded new metaphors, new mathematics, new humility. To study the cosmos was no longer to chart stars against the sky, but to confront the very structure of reality, to ask whether time itself had meaning beyond the temporary flicker of civilizations and suns. Even as telescopes grew sharper in theories, more precise, the haunting uncertainty remained. Humanity was beginning to see not only the immensity of space, but the fragility of its own existence within it. The fate of the universe was not a question apart from human life. It was a reflection of it. Every model of cosmic destiny was also a mirror, showing what it meant to live in a universe that may collapse, may fade, or may cycle forever. Thus, in the early attempts to predict the cosmos's end, one sees not merely the cold workings of mathematics, but the first stirrings of a deeper truth, that science, in its pursuit of understanding, had stepped across the boundary between observation and wonder. The universe was no longer only the backdrop of existence. It was the greatest story ever unfolding, a mystery still becoming, with humanity at once spectator and participant in its endless drama. The late 20th century carried within it a revelation as profound as any in the history of science. For decades, astronomers had charted galaxies drifting apart, their recession speeds faithfully echoing Hubble's law. Many assumed that gravity, the silent hand of attraction, would gradually slow this expansion. The cosmos might expand forever, or it might eventually collapse. But in either case, the rhythm of destiny seemed tethered to gravity's restraint. Then came the shock of 1998. Two independent teams, led by Saul Brian Schmidt and Adam Rees, studied distant type Ia supernova, brilliant explosions of dying stars that serve as cosmic mile markers. Their flickering light, stretched across billions of years, carried with it a message no one expected. The universe was not slowing, it was accelerating. Galaxies were being pushed apart faster and faster, as though some hidden force was woven into the very fabric of space itself. That force, mysterious and implacable, came to be called dark energy. It was not matter, nor radiation, nor anything familiar. It was a pressure that worked in defiance of gravity, an invisible hand pulling the universe outward. Today, it appears to dominate the cosmos, making up nearly 70% of its total content, and yet it remains unknown, a placeholder name for an enigma that challenges the very foundations of physics. With this discovery, the question of fate was transformed. No longer a simple contest between gravity and expansion, it became a struggle between visibility and invisibility, matter and void, the known and the unknown. If dark energy remains constant, the universe will expand forever, growing colder and lonelier until galaxies vanish beyond reach. If it grows stronger, the expansion could rip apart not just galaxies, but stars, planets, and even the atoms themselves in a big rip. If it weakens or reverses, the cosmos might still collapse, ending in fire rather than frost. The future, once thought predictable, became uncertain again. This accelerating expansion introduces another haunting limit, the cosmic event horizon. Just as black holes possess horizons beyond which no light can escape, so too does the universe itself now carry a horizon born of acceleration. Beyond a certain distance, the expansion is so rapid that light from those regions will never reach us. Entire galaxies, billions of them, are already slipping silently beyond visibility. their light stretched into oblivion by the swelling of space. What remains accessible to observation is shrinking, not because the universe is smaller, but because its expansion outruns perception. Humanity now gazes into a cosmos where much of reality is forever beyond reach. Black holes mirror this paradox on a smaller stage. Within them, gravity crushes matter to densities so extreme that space and time themselves collapse. At their center lies a singularity where equations break and comprehension falters. In this way, a black hole is a microcosm of the universe's ultimate questions. What happens when space-time reaches its limit? What lies beyond the horizon of collapse? The study of black holes, from Hawking radiation to the Event Horizon Telescope's first images, has become inseparable from the study of the universe's own boundaries. Each black hole whispers of an edge where physics strains against mystery. Yet the most daunting edge lies not in the distant future, but in the ancient past. To ask what occurred at the very beginning is to confront Planck time, the unimaginably brief instant. Why -43 seconds after the Big Bang, when the universe was so dense and hot that relativity and quantum mechanics could no longer be separated? Beyond this threshold, equations dissolve, and science peers only into speculation. Quantum cosmology attempts to push further, suggesting that space and time themselves may be emergent, rising from a deeper order not yet understood. Some theories speak of a quantum foam, a restless sea of probabilities from which the cosmos was born. Others imagine a multiverse, where countless realities bubble into being beyond our horizon. None can yet be proven, but all press against the walls of understanding. And in the present day, humanity has begun to listen to the universe in an entirely new way. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime itself, generated by the collision of two black holes more than 1 billion light-years away. For the first time, gravity was not inferred but heard, like a faint echo from the deepest caverns of reality. These waves confirm Einstein's predictions, but more than that, they open a new frontier. With gravitational wave astronomy, the universe may reveal secrets that light alone cannot carry, whispers from the earliest moments, or signals from horizons otherwise shrouded. The extreme edge of science lies here, in the acceleration that drives galaxies apart, in the horizons that erase parts of reality from view, in the singularities that swallow space-time, in the quantum flicker of creation, and in the waves that ripple through the cosmic sea. Each discovery expands knowledge while deepening mystery. Each observation reveals the fragility of certainty. The story of the accelerating universe is not only a revelation about fate, it is a reminder that the cosmos does not yield its answers easily. It is vast, elusive, and unafraid to leave humanity gazing into questions without end. In searching for the limits of space and time, science has found only horizons, boundaries, that move further the closer they are. Approach the acceleration of the universe is not only a scientific revelation, but also a profound shift in how existence itself must be imagined. For centuries, cosmology assumed a universe governed by symmetry, galaxies like dancers on a stage, their movements dictated by the balance of matter and gravity. The discovery of dark energy shattered that expectation. The cosmos is not merely drifting apart, it is racing, and that race is quickening with time. The expansion is not a gentle tide, but a restless surge, driven by a force more dominant than stars, gas, or even dark matter. This deepens a truth that unsettles the imagination. What we call the observable universe is not the whole, but a dwindling island of visibility. With every passing billion years, galaxies that shine in our telescopes today will fade beyond detection. Their light will never again cross the widening gulf of space. Already distant clusters are stretched into obscurity, their photons lengthened into radio whispers so faint that they dissolve into the cosmic background. The night sky, once thought eternal, is slowly being erased. Future astronomers, born trillions of years from now, may live in a cosmos stripped of evidence, surrounded only by a dim halo of local stars. To them, the universe may appear empty, its true history lost to the horizon. This vanishing of the visible is not merely an astronomical curiosity. It is a philosophical wound. It confronts the mind with the realization that perception is temporary, that knowledge itself is bounded by horizons we cannot escape. Just as ancient sailors once stood at the shore, unable to imagine countenance beyond the sea, humanity now stands at the edge of a cosmic ocean where most of its waters are already hidden. Black holes sharpen this paradox into a single point. Their horizons mimic the universe's own, an invisible threshold where information is locked away. Hawking's insight that black holes evaporate, slowly releasing their mass as faint radiation, offers the tantalizing suggestion that no horizon is absolute. Yet the paradox remains unsolved. What becomes of information swallowed by the singularity? If it is lost forever, then the laws of physics themselves fracture. If it is somehow preserved, hidden in subtle correlations of radiation, then reality is more intricate than imagination has yet conceived. In both cases, black holes stand as laboratories of the extreme, where the fates of particles and the fates of universes converge to peer further. One must descend into the quantum fog of creation. At Planck's scales, where time itself is sliced into intervals smaller than thought can grasp, the structure of space-time may cease to be smooth. Theorists picture it as a foam, a restless turbulence where particles flicker into and out of existence, and where geometry itself is uncertain. Here, the comforting fabric of cause and effect begins to unravel. Some models suggest that the Big Bang was not a beginning, but a transition, a bounce from a prior collapse, or the branching of one universe into many. Others speak of eternal inflation, where quantum fluctuations generate endless bubble universes, each with its own laws, hidden forever beyond reach. These possibilities, though speculative, are not idle dreams. They arise from equations written to reconcile relativity with quantum mechanics, from attempts to unify the vast with the small. In the clash between the cosmic and the subatomic lies the frontier of knowledge, a place where human reason pushes against the boundaries of comprehension. It is there, in the mathematics of strings, loops, and multiverses, that scientists seek a glimpse of what came before time itself, and still, the universe whispers through experiment. The detection of gravitational waves by LIGO was more than a triumph of engineering. It was an opening of a new sense. With each tremor of space-time recorded, humanity hears the universe narrate its own history. Black holes colliding, neutron stars merging, cataclysmic events unfolding across billions of light-years. Soon, more sensitive detectors may capture waves born in the earliest moments after the Big Bang, vibrations that ripple directly from the universe's birth. Unlike light, which is blocked or scattered, gravitational waves pass unhindered, carrying an unbroken record of origin. To detect them is to listen to the first heartbeat of time. In this way, the acceleration of the universe is not only a revelation of doom or distance, it is also a gateway, a reminder that even as horizons advance, new windows can open. Light vanishes, but gravity sings. Galaxies recede, but waves echo. Horizons may conceal, but they also inspire deeper inquiry. At the extreme edge of science, knowledge becomes a paradox. The more the universe is mapped, the larger the unmapped becomes. The more precise the measurements, the greater the mystery revealed. In this, there is a kind of symmetry, after all, a balance between understanding and wonder. The cosmos offers truths, but always in fragments, as if to remind its observers that certainty is fleeting, and humility eternal, the accelerating universe, the dark energy that drives it, the horizons that erase the visible, the singularities that swallow the known, the quantum foams that blur the foundation. These are not separate tales, but facets of the same riddle, a riddle that stretches across time, from the first instant of being to the last flicker of light, and in its telling, it reveals not only the fate of galaxies, but the limits of knowledge itself. The universe, vast and ancient, does not simply invite curiosity about its origins, it demands questions about its fate. For as surely as it began in fire, it will end in silence. The night sky, glittering with stars, is not eternal. It is a fleeting stage of cosmic history, a brief window when matter burns brightly against the dark. Scientists, staring into the abyss of time, have pieced together theories of what will come when this window closes. Each theory is rooted in mathematics and observation, yet each carries with it a weight of philosophy, a reflection on how existence itself dissolves. The most widely accepted scenario is known as heat, death, the quiet exhaustion of the cosmos. It is a vision shaped by thermodynamics, by the relentless growth of entropy, the measure of disorder. As stars consume their fuel, as galaxies burn through their reserves, the universe drifts into a state where no gradients remain, no flows of energy to power change. Trillions of years from now, galaxies will dim. The last stars will be faint red embers, and then black dwarfs, cinders of once shining suns. Black holes will dominate for a time, swallowing matter and radiation until even they, too, evaporate through Hawking radiation. What remains is not fire nor collapse, but an eternal dusk, a thin haze of particles stretched across an expanding void. Time continues, but nothing happens. Motion without meaning, change without difference. The heat death is not a singular moment of ending, but an infinite twilight. Unlike the apocalyptic imagery of fire or collapse, it is quiet, almost gentle, the death not of a creature, but of a flame, fading into darkness too vast to measure. Yet in its gentleness lies its terror, a universe not ending in drama but in stillness, a silence that lasts forever. But physics entertains other possibilities. Some equations, when tilted toward a darker interpretation of dark energy, reveal the Big Rip. Here, the very fabric of space accelerates without limit, tearing apart not just galaxies, not just stars, but the atoms themselves. Galaxies first drift apart, then stars are ripped from their orbits, planets pulled from suns. Later, even molecules and atoms are shredded as the expansion of space overwhelms the bonds that hold matter together. In this scenario, the universe does not fade into coldness. It fractures in violence. At some finite moment in the future, everything from the largest cluster of galaxies to the smallest speck of matter is torn asunder. Nothing survives. Not even the structure of space-time remains coherent. It is a vision of annihilation, a cosmic unweaving of the tapestry itself. Other scientists hold to the possibility of the opposite, that the universe might one day halt its flight and reverse course. This is the big crunch, where the expansion slows, then stops, and gravity seizes control. Galaxies would drift closer, stars collide, and heat rises as matter collapses back into a cosmic fireball. In this scenario, the end looks like the beginning, a singularity of unimaginable density and temperature, perhaps the seed of a new cycle. Some versions of this theory propose an oscillating universe, a rhythm of big bangs and big crunches, a heartbeat across eternity. If true, the universe would not die but endlessly renew, each collapse giving birth to a new creation, each creation destined to fall again. It is a poetic symmetry, yet one that current observations do not favor. Today's data points elsewhere. The accelerated expansion measured by Type Ia supernova, confirmed by mapping the cosmic microwave background and the clustering of galaxies, suggests a cosmos that will not fall back. Dark energy appears too strong, too persistent, for gravity to reverse its pull. This expansion does not rip apart atoms, not yet, not at its current strength, but it does carry galaxies away, faster than light, beyond the horizon of visibility. This is the horizon freeze, the slow disappearance of the universe into isolation. Galaxies recede, their light stretched into invisibility until only the nearest cluster remains. To future observers, the universe will appear smaller, lonelier, emptied of its true scale. It is here that cosmology turns philosophical, for in each of these fates, heat, death, rip, crunch, freeze, lies a confrontation with limits. The universe is not a static stage, not an infinite and eternal backdrop for life and matter. It is fragile, evolving, with futures that dwarf human timescales, yet carry implications for every thought, every existence. What does it mean to live in a cosmos destined for silence? What does it mean to build civilizations in a universe where all stars eventually die? The mainstream theories agree on one truth. The universe is not immortal. Its grandeur has a trajectory. Its beauty has a horizon. And yet, in the very act of predicting its end, science deepens the wonder of the present. The stars above are temporary, but precisely because they are temporary, their light is precious. The universe's fate, though hidden far beyond human lifetimes, can be traced across unfathomable spans of time. Each mainstream theory carries with it not only a vision of how things end, but also a timeline of how the transition unfolds. A gradual erasure written across trillions of years. In the path toward heat death, the stars themselves mark the first chapter of decline. Already, more than 90% of the stars that will ever shine have been born. Over the next 100 trillion years, stellar nurseries will fall silent, their clouds of gas and dust consumed or dispersed. The cosmos will belong to long-lived red dwarfs, small, faint suns burning slowly in the dark. They will flicker for trillions of years, outlasting the giants of today's sky, but even their patience has a limit. One by one, they too will fade, leaving behind only black dwarfs cold, dark remnants invisible to any future. Beyond that epoch, galaxies will lose their cohesion. Without new stars to illuminate them, they become cemeteries of corpses, neutron stars, white dwarfs, and black holes drifting in silence. Encounters between these remnants will sometimes trigger cataclysms, collisions, bursts of radiation, but such events grow rarer as time stretches on. Gravity itself begins to scatter what remains. Over tens of quadrillions of years, stars and remnants are ejected from their galaxies, leaving only solitary wanderers adrift in infinite night. Then, black holes inherit the universe. For a span of unimaginable length, they are the last actors on the cosmic stage. They consume whatever strays too close, but even they cannot endure forever. Quantum theory predicts that black holes slowly leak energy through Hawking radiation, a trickle of heat escaping their event horizons. For supermassive black holes, this process takes 10,100 years, a timescale so vast it defies comparison. When the last black hole evaporates, only a diffuse glow of particles and radiation will remain, stretched across an endless void. This is the final silence of heat death. No stars, no galaxies, no structures, only entropy maximized. The cosmos, at absolute equilibrium. The Big Rip follows a different chronology. In this vision, the clock runs faster, not slower. If dark energy strengthens with time, expansion accelerates exponentially. First, galaxy clusters are torn apart, their gravity too weak to resist the stretching of space. Then galaxies themselves unravel, their stars scattered. Closer to the end, stars are stripped of their planets, planetary systems destroyed. As the catastrophe accelerates, even atoms cannot hold together. The electromagnetic force, the glue of matter itself, loses its grip under the pressure of expansion. In the final moments, mere seconds before the universe rips itself apart, quarks and leptons are torn from each other, and space-time itself dissolves. Unlike the slow fading of heat death, the Big Rip is violent and abrupt, an end not of silence, but of shattering. The Big Crunch, in contrast, is a return to fire. In this scenario, expansion is not eternal. It halts and reverses. Over eons, galaxies stop receding and begin converging. The night sky brightens as galaxies crowd closer, collisions becoming common, until the universe itself collapses inward. Temperatures rise, densities soar, and the cosmos grows hotter and smaller with each passing age. In the final moment, everything converges into a singularity, a mirror image of the beginning. Some physicists suggest that from this singularity, a new Big Bang might erupt, not an end, but a rebirth. The universe could be one in a series of cycles, each collapse seeding a new creation. The horizon freeze, however, unfolds, almost imperceptibly. To civilizations observing billions of years from now, galaxies will vanish one by one as they slip beyond the cosmic horizon, carried away by expansion faster than light. Each galaxy that departs takes with it its history, its stars, its civilizations, all forever inaccessible. What remains is the local cluster, eventually bound into a single megagalaxy. To future astronomers, the universe will seem smaller and smaller until, at last, all evidence of its true vastness disappears. They will see only their own island of stars, floating in eternal darkness. The greater cosmos will be gone, not because it ceased to exist, but because its light could no longer reach them. Present-day evidence leans toward heat death or horizon freeze. Measurements of the cosmic microwave background, of supernova, and of galaxy clustering all point to an accelerating universe, one not destined to collapse. Yet whether that acceleration remains constant or grows stronger will decide between the eternal fading of heat death and the catastrophic tearing of the Big Rip behind. Each scenario lies an unspoken truth. The end is as mysterious as the beginning. Science peers forward with equations and observations, but the distant future remains a landscape of shadows, shaped by forces barely understood. Dark energy, the driver of acceleration, makes up nearly 70% of the universe, yet its nature is still unknown. If it changes, even slightly, the fate of the cosmos changes with it. Thus, the universe balances between visions of silence, violence, collapse, or erasure. Each theory paints a different horizon, but all share a single theme. Nothing lasts forever. Stars, galaxies, even space-time itself are impermanent. The cosmos, so vast and eternal to human eyes, is itself transient. Its destiny is not static, but evolving, written in equations that stretch across billions of years. And in contemplating these ends, one is drawn back to the present. The night sky is no longer just a view into space, but a glimpse into time, into a fleeting chapter in the universe's long story. To witness stars at all is to live in a privileged age, a middle act between the fire of the beginning and the silence of the end. The search for the universe's fate has never been confined to the boundaries of observation. Beyond the steady march of mainstream theories lies a realm where imagination and mathematics entwine, where speculation stretches the fabric of known science into shapes both daring and strange. If the heat death and the Big Rip chart the predictable paths of entropy and acceleration, then these speculative visions attempt to pierce through the horizon of understanding itself, not merely asking how the universe will end, but whether the concepts of end and universe even apply. Eternal inflation is one such vision, born from attempts to explain why the cosmos appears so uniform on its largest scales. Inflation, the theory that the universe expanded exponentially in its first instant, predicts a consequence far stranger than smoothness. If inflation can occur once, it need not ever truly stop. Quantum fluctuations could spark new regions of space to inflate endlessly, creating bubble universes adrift in a larger multiverse. In this picture, what is called the universe is only one bubble among an infinite froth, each with its own laws of physics, its own constants, perhaps even its own dimensions of time and space. Some bubbles may allow stars, planets, and life. Others may remain sterile, governed by laws unrecognizable. Here, the word end dissolves, for if universes are eternally budding off into infinity, there may never be a final horizon. Instead, existence itself becomes a ceaseless flowering without conclusion. Yet not all visions point toward endless branching. Some suggest a cycle, a rhythm pulsing through eternity. The Big Bounce carries echoes of ancient myth, reimagined in equations of modern cosmology. Instead of a singular beginning, the universe may expand, slow, collapse, and rebound, oscillating forever in cycles of creation and destruction. Each crunch sows the seeds for a new bang, and each bang leads inevitably to another collapse. In this cosmic heartbeat, time has no ultimate origin or conclusion, only an eternal cadence. But the details are fraught with difficulty. Quantum gravity, still elusive, would be needed to fully describe the transition between collapse and rebirth. Until then, the Big Bounce remains, a vision glimpsed dimly through the haze of incomplete physics, tantalizing, but uncertain. From this notion of cycles arises another, more radical proposition, conformal cyclic cosmology, proposed by mathematician Roger Penrose. In this view, the end of the universe is not collapse, but transformation. As heat death erases structure, as black holes evaporate and particles disperse, the universe cools into uniformity. And when all scales of time and distance lose meaning in such a perfectly smooth expanse, the end becomes mathematically indistinguishable from the beginning. A new universe, a new eon, emerges not through a violent rebound, but through a subtle redefinition of what space and time mean at the extremes. Each cosmos, then, is the ghost of its predecessor, carrying forward not matter, but patterns. Perhaps even faint whispers of ancient structures preserved in the background radiation. Other theories strike at an even deeper question. Perhaps the universe itself is not what it appears to be. The holographic principle, inspired by black hole physics, suggests that the three-dimensional universe may be a projection of information encoded on a two-dimensional boundary. Just as a hologram on a surface can give rise to an image with depth, reality itself might be a shadow cast by a more fundamental structure. In such a framework, the edge of the universe is not a spatial frontier, but an informational one, the totality of bits written on a cosmic boundary beyond perception, pushing further still. Some speculate that the cosmos is not only informational but computational. Simulation theory proposes that the fabric of reality could be the output of a vast underlying program, its rules set not by natural law but by code. Two observers within the simulation, space, time, and physics, would feel no less real than in a base reality. The end, in such a scenario, would be neither heat death nor collapse, but the halting of the program, or perhaps its infinite continuation, with universes running like countless experiments across unimaginable substrates. Such ideas blur the line between science and philosophy, for they challenge not just what the universe is made of, but what it means for it to exist at all. If space and time are emergent, born from deeper layers of mathematics or information, then asking about their end may be like asking about the end of a mirage. The limits would not be physical horizons, but conceptual ones. Perhaps space and time are not fundamental realities, but tools of perception, the stage on which existence is played. The final frontier, in this view, may not be reached by traveling outward, but by peeling back the assumptions of reality itself. And so the speculative edge of cosmology reflects a deeper truth about human inquiry. At the limits of knowledge, imagination fills the silence, guided by equations, experiments, and philosophical wonder. Each theory, whether eternal inflation or the holographic principle, reveals not certainty but possibility, glimpses of what reality might be when stripped of familiar boundaries. In contemplating these visions, one recognizes that the question of the universe's end may be inseparable from the question of its nature. At the edge of speculation, science becomes inseparable from philosophy, and the universe begins to resemble a hall of mirrors, where every reflection raises more questions than it answers. What emerges is not a singular narrative of endings, but a spectrum of possibilities, each reshaping the meaning of existence itself. If eternal inflation paints reality as an infinite multiverse, then it also forces the unsettling notion that anything that can happen must happen somewhere. In an infinity of universes, every configuration of matter, every history, every life might be repeated endlessly, each variation branching into new domains. Somewhere, a universe identical to this one may unfold, while elsewhere, entirely alien realities emerge with laws so foreign that human thought cannot imagine them. The end in such a vision is an illusion, for infinity admits no closure. What humans call an ending is only the boundary of perception, not of existence. The Big Bounce and cyclic cosmologies carry a different burden of meaning. They suggest that creation itself is not a singular miracle, but a recurring rhythm. Stars, galaxies, civilizations, all may rise and fall countless times, their echoes lost in each rebirth. For some, this idea brings comfort, a sense that nothing is ever truly final. For others, it evokes futility, a repetition without memory, where each universe forgets the last. Here, the end is not a curtain falling, but a reset, an eternal return to beginnings, stripped of history. Penrose's conformal cyclic cosmology deepens this reflection by suggesting that traces of past universes may not be erased entirely. Within the faint patterns of the cosmic microwave background, he proposes there could be Hawking points, subtle imprints from black holes evaporating in a prior eon. If such signatures exist, then the universe itself may be a palimpsest, a manuscript written and rewritten across epochs, each story layered over the faint ink of the last. In this framework, the end of one universe is not a void, but a bridge, its final breath woven quietly into the fabric of the next. The holographic principle moves further still, dissolving the distinction between space and information. In this view, every galaxy, every star, every conscious thought is encoded on a boundary beyond reach, projected into the three-dimensional stage of perception. If reality is holographic, then the edge of the universe is not measured in kilometers, but in bits of information. The vast cosmos may be nothing more than a cosmic ledger, storing the story of existence in mathematical symbols inscribed upon an unseen horizon. In such a universe, the end would come not through heat death or collapse, but through the erasure or corruption of information itself, a cosmic silence, not of space, but of memory. Simulation theory takes this informational vision to its most radical conclusion. If the cosmos is computation, then stars are data structures, galaxies algorithms, and time itself the ticking of an unseen processor. The universe may end not in collapse or cold, but with the shutdown of the system that runs it, or with its indefinite continuation across endless cycles of calculation. Within this possibility lies a profound inversion. The search for cosmic limits may not reveal the structure of matter at all, but the logic of code, the architecture of an intelligence beyond comprehension. Each of these speculative frameworks invites a different confrontation with the concept of finality. If the cosmos is infinite, there is no end. If it is cyclic, endings are preludes. If it is holographic, the end is a dissolution of information. If simulated, it is a matter of termination or continuation. And if conformal cyclic cosmology is true, then the end is an indistinguishable new beginning. What unites them all is a recognition that human thought is bound to metaphors of time and space, while reality may transcend them. The word end itself may be a construct of limited perception, a reflection of finite lifespans projected onto the infinite. The universe, in its most profound mysteries, might not admit such boundaries at all, as science presses deeper into the unknown. These speculative visions remain on the frontier between testable theory and philosophical wonder, yet even if unproven, they serve a purpose. They remind humanity that the search for the universe's fate is not only about equations and observations, but about perspective, about confronting the possibility that space, time, and existence itself are not what they seem. And in that confrontation lies, perhaps, the deepest mystery of all, that the universe's end may never be discovered, not because it is hidden, but because it may not exist in the way the human mind imagines it. The journey outward becomes, ultimately, a journey inward into the limits of thought, the boundaries of imagination, and the fragile meanings carved from the infinite silence of the cosmos. In the quiet immensity of the cosmos, humanity stands at the shoreline of knowledge, gazing outward into the darkness with tools of glass, metal, and mathematics. Each instrument becomes a kind of time machine, peeling back the layers of history written in starlight, and each discovery carries the weight of questions that reach toward the universe's ultimate fate. The James Webb Space Telescope now drifts in its cold orbit, a sentinel stationed far from Earth, its mirrors unfolding like petals of a metallic flower. It peers into wavelengths invisible to the human eye, capturing photons that have traveled for over 13 billion years. These faint threads of light come from galaxies so distant that they formed when the universe was still in its infancy, less than a few 100 million years after the Big Bang. In their shapes and clustering, scientists search for patterns that might reveal how cosmic structure emerged, how stars ignited for the first time, and perhaps how the story of the universe's future is inscribed in its earliest chapters. But telescopes alone cannot untangle the deepest mysteries. On Earth, beneath layers of stone and steel, immense particle colliders recreate the conditions of the primordial universe in controlled bursts of energy. At CERN, protons are accelerated to near-light speeds and smashed together, releasing fragments that briefly expose the quantum machinery of reality. These collisions are not mere experiments of curiosity. They are attempts to glimpse the hidden frameworks of nature, the strange shadow of dark matter, the elusive fingerprint of supersymmetry, the subtle whispers of quantum gravity. Each particle, each trace on a detector, becomes a clue pointing toward whether space and time themselves are emergent phenomena, born not from geometry, but from something deeper, more abstract, and more profound. The quest does not stop at the edge of what exists now. It stretches into visions of what humanity might yet create. Future missions, colossal in ambition, delicate in design, promise to extend the reach of human senses further still. LaVoie, a proposed space telescope with a mirror vast enough to resolve alien atmospheres, may also map the cosmic web in exquisite detail, tracing the dark scaffolding upon which galaxies cling. LISA, a space-based gravitational wave observatory, will listen not with eyes but with ears, attuned to ripples in space-time itself, from the slow merging of black holes to the possible tremors left behind by the Big Bang. It may hear the faint echoes of creation, vibrations that outlived stars and galaxies alike. Alongside these instruments, another force rises, not built of steel or glass, but of thought woven into algorithms. Artificial intelligence now shapes simulations of the universe with increasing precision, evolving virtual galaxies across billions of years in moments of computation. These models test competing theories of dark matter, dark energy, and cosmic expansion, searching for the subtle distinctions that observation alone cannot yet confirm. In their virtual skies, stars are born, spiral arms twist, and black holes devour, all governed by equations written by human hands, but expanded into outcomes too vast for human intuition to track unaided. AI becomes a bridge between imagination and reality, allowing the cosmos to be rehearsed and replayed in countless variations. Yet even with these expanding powers, the deepest debates remain unsettled. Some physicists follow the path of string theory, envisioning tiny vibrating filaments whose harmonies give rise to particles, forces, and even the dimensions of space itself. Others turn to loop quantum gravity, a framework where space-time is granular, woven from indivisible loops that bind together into the fabric of reality. Between them lies the search for a unifying principle, a key that might unlock the riddle of how the infinite cosmos emerges from the finite dot. In these debates, in these instruments, in these collisions of protons and of theories, lies a paradox. Humanity cannot journey physically to the end of time, nor to the beginning. Yet through mathematics, imagination, and the light of ancient stars, it travels there in thought. Numbers become vehicles, equations turn into voyages, and each scientific model becomes a symbolic passage across gulfs, unreachable by spacecraft. The work continues not only because the universe is mysterious, but because it is inexhaustible. Every discovery opens into more profound unknowns. The first galaxies revealed by James Webb are stranger than expected, larger, brighter, and more evolved than theory predicted. Each particle collision at CERN whispers of forces unseen. Each new mission, envisioned by engineers and astronomers, expands the horizon of possibility. And so, humanity's search for the fate of the universe is less a march toward an answer, and more a symphony of questions, a song written across time, composed in fragments of light and matter, sung through machines that amplify the senses and extend the reach of thought. In the end, perhaps the universe cannot be captured by any single theory or observation. Perhaps its destiny is not to be solved, but to be continually revealed, a horizon that recedes as it is approached, forever urging the mind deeper into the unknown. The search for the universe's fate unfolds as a dialogue between silence and discovery, between the deep unknown and the fragile persistence of human curiosity. Each step forward in science is measured, not only in data but in perspective, in how humanity situates itself within a cosmos that resists finality. As telescopes widen their gaze and colliders plunge deeper into the invisible, The line between observation and philosophy grows ever thinner. The James Webb Space Telescope, with its crystalline mirrors, does not merely gather light. It collects time itself. Each photon it captures has wandered across billions of years, a survivor from a vanished age. In those pale signals lie hints of the universe's first structures, and within those structures, perhaps the faintest fingerprints of the laws that will determine how it all will end. If galaxies form earlier, if matter clusters differently, if the expansion unfolds faster than expected, these subtleties ripple forward, cascading into different versions of the future. Meanwhile, underground laboratories and cosmic observatories seek the particles that remain hidden, shaping the scaffolding of galaxies yet unseen. Dark matter has never been touched, never been isolated in a detector, but its gravitational influence sculpts the cosmos like an unseen hand. To understand dark matter is to approach one of the most fundamental keys to cosmic fate, for the density and distribution of this invisible substance determine how galaxies will evolve, how clusters will bind, and whether the great expansion will one day falter or continue without end. Dark energy, stranger still, lurks not in clustering but in emptiness. It is the name given to an observed acceleration, a quiet pressure woven into space itself. Its nature is unknown. It could be a property of the vacuum, an energy of space-time, or the influence of hidden dimensions. Whatever its origin, it defines the rhythm of the cosmos at the grandest scale. If its strength shifts over time, the future could splinter into radically different destinies: eternal acceleration, violent disintegration, or a slowing collapse. Every new measurement, from supernova, from baryon acoustic oscillations, from the faint glow of the cosmic microwave background, sharpens the map of what tomorrow might hold. Even as it deepens the sense of mystery, the frontier stretches further still into waves that cannot be seen at all. Gravitational waves, first directly detected in 2015, revealed that space-time itself can tremble like the surface of a pond. Future missions, like LISA, will extend this hearing into lower frequencies, attuned to signals from the earliest cosmic moments. Perhaps buried in those waves are echoes from inflation, a storm of exponential growth that may have birthed the observable universe. If such signals are ever captured, they would not only rewrite the story of beginnings, but also hint at what remains possible for the end. Even as instruments grow more powerful, the role of simulation becomes inseparable from exploration. Supercomputers trace the paths of trillions of particles across billions of years, crafting universes in miniature. In these models, dark matter filaments weave into webs, galaxies ignite and extinguish, black holes collide and merge. By comparing these digital cosmoses with what telescopes record, scientists test whether their assumptions about the laws of nature truly mirror reality. Yet simulations also press into realms that instruments cannot yet reach. They forecast conditions trillions of years ahead, long after stars are gone, long after even black holes have evaporated. These visions are not prophecy, but they extend imagination into a space where observation cannot yet follow, mapping out scenarios for a universe grown cold and silent and still. Questions linger at the threshold of theory. String theory suggests that the universe is woven from minuscule vibrating threads, each vibration giving rise to particles and forces, perhaps even to the dimensions of space and time themselves. Loop quantum gravity envisions space-time not as continuous but as granular, woven from finite units that shimmer at the Planck scale. Competing, incomplete, both strive for a union of quantum mechanics and general relativity, a marriage of the very small and the very vast. Without such a synthesis, the universe's deepest destiny remains unknowable, suspended in paradox. For all the complexity of these pursuits, The essence of the endeavor carries a simple truth. Humanity seeks not only to predict, but to understand, to find meaning in the silence between stars. Instruments may capture photons and particles, but it is human thought that turns them into stories, into questions of beginnings and endings, into reflections of existence itself. The current efforts do more than probe cosmic mechanics. They reveal a mirror. In searching for the fate of the universe, humanity uncovers the fragility of its own moment. On a cosmic scale, civilizations are fleeting, stars are temporary, galaxies themselves dissolve. To grasp this truth is not despair, but clarity. For even in a universe that may one day fade into entropy, the act of understanding it transforms the fleeting into the eternal. In this sense, each observatory, each experiment, each collision of particles becomes more than science. They are gestures of defiance against the silence, reminders that even in a universe destined for darkness, sparks of awareness can illuminate meaning. The quest is unfinished, perhaps unfinished, yet it continues across mirrors that unfold in the void, across machines that thunder beneath the earth, across minds that model what cannot yet be seen. Humanity journeys to the edge of time not with ships, but with questions. And in those questions lies its truest voyage. The universe, vast and indifferent, stretches across distances and times so immense that even the longest human histories dissolve into a blink. Against this backdrop of infinity, the question of endings carries a weight unlike any other. If the cosmos itself has a fate, if stars will extinguish, galaxies will vanish, and even time will surrender to entropy, what then does it mean to exist, briefly, within such a story? For humanity, the awareness of impermanence is not new. Long before telescopes pierced the night, civilizations spoke of endings in the language of myth. The Norse envisioned Ragnarok, a twilight of the gods when fire and ice would consume all. Ancient Hindus told of kalpas, vast cycles of creation and destruction, in which universes themselves were born, perished, and renewed. In the deserts of the Near East, prophets imagined apocalypses where history bent toward judgment and rebirth. These visions, though bound to culture, carried a resonance that modern cosmology unexpectedly revives. For when science describes a heat death, a big rip, or a cosmic rebirth, it echoes a timeless human instinct to imagine closure, to give shape to an ending, even when that ending lies beyond sight. Yet the universe's timeline is mercilessly disproportionate. Stars will burn for billions of years. Black holes will evaporate across spans of time so immense they defy imagination. And eventually, if the heat death comes to pass, the cosmos will linger in silence trillions of years beyond any human trace. Against this scale, a human life, even the rise and fall of civilizations, is smaller than a grain of dust in a desert that has no horizon. This confrontation brings both humility and meaning. On one hand, it diminishes human significance. Nothing of our daily struggles seems to matter when weighed against galactic collisions or the death of starlight. On the other hand, it magnifies the preciousness of the moment. To exist at all, here, on a fragile world orbiting an ordinary star, in a universe still alight with galaxies, is to occupy a fleeting but miraculous window of cosmic vitality. Humanity lives in an age when the night sky is still bright, when constellations still map the heavens, when telescopes can still glimpse the faint glow of creation itself. That window will not last forever, but within it lies everything that can be known, imagined, and cherished. The search for the universe's fate, then, is more than a scientific pursuit. It is a reflection of human limitation and desire. To ask whether the cosmos will freeze, collapse, or cycle eternally is to reveal a deeper truth, that the act of questioning may matter more than the answer. The universe does not require meaning, but human beings do. And so, they stretch mathematics to its limits. They launch instruments into the abyss. They simulate futures trillions of years away. Not because they will witness the end, but because to imagine it is to affirm what it means to be conscious, to glimpse, however briefly, the shape of eternity. Perhaps the end of the universe will never be known. Perhaps its horizon will remain forever hidden, like a shoreline glimpsed across an unreachable sea. Yet the yearning to see beyond it defines humanity as much as its art, its memory, and its compassion. In this sense, the quest is not in vain. Even if silence awaits, the questions themselves have become part of the universe's story. In the end, cosmology becomes a mirror. It shows that the greatest boundary may not be the edge of time or the death of stars, but the limits of human comprehension itself. And still, within those limits, the desire to reach further persists. That persistence, fragile, luminous, and fleeting, is humanity's own defiance against cosmic impermanence. If one day the stars fade, if galaxies drift beyond sight, if time itself thins into stillness, the universe will fall quiet. But the questions asked here, in this brief age of light, will remain inscribed in its fabric, not as words, not as monuments, but as the echoes of thought that once dared to wonder. In that echo lies a kind of immortality, not of bodies, nor of civilizations, but of curiosity itself. And so the story closes, not in despair, but in reflection. For even if the universe ends in silence, the act of questioning ensures that humanity's voice, however small, has touched eternity. The thought of endings, though shrouded in mystery, pulls humanity into an ancient dialogue between fragility and infinity. Every culture has wrestled with mortality, with the silence that follows life, and cosmology now extends that same question outward to the stars themselves. What does it mean that even the universe, the cradle of galaxies, the author of time, may carry within it the seeds of its own demise? For some, the prospect is unsettling, for it confronts the instinct to imagine permanence. Humanity is accustomed to boundaries, to seasons that return, to lives that begin and end, to landscapes that seem unchanging. Yet cosmology speaks of horizons receding forever, of energy dissipating until nothing remains to fuel the fires of existence. To envision such futures is to confront a scale of impermanence beyond ordinary comprehension, and yet the mind responds, not with surrender, but with imagination. If the cosmos drifts toward heat death, an eternity of cold, of atoms stretched thin and motionless, then every heartbeat today becomes infinitely more meaningful. If dark energy tears space apart in a distant big rip, then the brief era in which galaxies shine together becomes a singular chapter in the story of everything. Even if the universe should collapse back into a singularity, it suggests a rhythm, a cosmic breath of expansion and contraction, into which human existence has been woven for one fleeting inhalation. The reflection reaches deeper still. It is not only a matter of cosmic scales, but of human identity. To ask about endings is to uncover a paradox, that beings so small, on a planet so fragile, can nevertheless imagine the fate of the universe itself. No other creature known can contemplate the death of time, nor speculate on cycles of eternity. This capacity to imagine, to project thought beyond survival, beyond the present moment, is itself a defiance against impermanence. The cosmos may end, but within it has arisen a species that dares to ask how ancient myths, too, reveal this impulse. In Mayan traditions, worlds rose and fell in cycles, with humanity reborn from the remnants of previous creations. In Buddhist cosmology, kalpas stretched across eons, universes arising and dissolving like waves on an endless ocean. In modern science, Inflationary models and cyclic universes whisper echoes of these visions. The difference lies not in the instinct, but in the tools, mathematics, telescopes, and quantum theories, replacing sacred stories and ritual. Both, however, spring from the same longing to map the edges of the unknown, and so a curious transformation occurs. Cosmology ceases to be only a science and becomes also a philosophy, a meditation on the place of human consciousness in a universe both infinite and impermanent. For while stars may burn and fade, questions remain. They are carried forward from the astronomers who first charted the stars, to the physicists who measure fluctuations in ancient radiation, to the philosophers who ask whether time itself is real. Each question becomes a thread in a tapestry that stretches as far as imagination allows. In this way, the end of the universe becomes less a conclusion than a reflection of the human condition. Mortality is shared across scales. A star dies, a galaxy fades, a universe cools, just as a human life flickers and falls silent. But within each span, meaning is forged. A single life can carry memory, create beauty, and ask questions that reach beyond the span of the cosmos. This parallel grants a strange comfort. The universe itself is mortal, and yet in its mortality it is wondrous. Thus the search for cosmic limits is never futile. Whether the future holds silence, collapse, or renewal, the act of seeking transforms the present. To measure the afterglow of creation, to chart galaxies near the edge of sight, to simulate the unfolding of trillions of years. These are not only scientific acts, but also affirmations of wonder. They declare that even in the face of endings, humanity chooses to ask, to imagine, and to reflect. If the cosmos ends in silence, it will not erase the questions. Those questions have already shaped the minds that asked them, the civilizations that pursued them, the fragile species that reached toward the stars. And in that sense, even a finite universe cannot diminish the infinite reach of curiosity. The final truth may be this, that the search for the universe's end is itself endless. Each discovery opens new horizons. Each horizon reveals deeper mysteries. The journey is not towards silence, but through it, and in traveling that path, humanity leaves behind the only echo it can, an echo not of permanence, but of wonder.